This is a topic I talked about several times. In some sense, I plan to, this will be one of the last times, because I want to give the challenge to other people to continue working on this problem. So the problem is very simple to formulate. Given a domain in Cn, and let's restrict ourselves to bounded domains. Let's assume that it has a smooth boundary. Of course, this can be formulated. And also, let's assume that omega is pseudoconvex. Then let's give ourselves a 0-1 form, omega on the domain, such that two things are satisfied. First, the bar omega is 0, and this is bounded. So omega is bounded. Well, omega, huh? That's the problem. And then you're asking, can we find some u such that d bar u is equal to omega? And of course, the main problem here is that this solution is also bounded. So now, of course, I'm running out of space right here. It's bounded by a constant times the sup-norm of omega itself. There should be an omega. No, I have a problem. I'm not made tall enough. And there should. Okay, so this is an old problem. In the 70s, there's several people, Henkin, Ramirez, and I'm sure I'm going to forget a whole lot of names, so let's just do like this. We're able to solve this if to find a positive answer. If omega is not just pseudoconvex, but it's strictly pseudoconvex. And since my talk will be a little bit inspired by the ideas, even though I'm not going to be able to do anything like they did, let me mention a little bit more about what they did and put it over there so that I can stay during the talk. They were able to actually construct an integral kernel that helped solve this problem. So they had their omega, and they found their u as an integral of the form omega. So here now I'm running into a problem, so let me just rename omega f here. Fortunately, because omega is going to play a little bit different role here. As a constant times integral over the boundary of omega across the unit interval. F wedge some form nu of wi wedge. See what I run into here. Omega suddenly had a different role. It's now going to play the role of the holomorphic volume form. And then an interior integral, which I'm not going to worry about because it always converges. The point here, the whole point here is that these wi's are now going to be made in a particular way. They're going to be lambda psi I minus ci, psi minus c squared, plus 1 minus lambda times hi of psi c. And the hero in this is these hi's, so I goes from 1 to n. And the heroes, as I said, are these hi's. They're holomorphic. And they solved a so-called Cauchy-von Tappe equation. Namely, the sum I goes from 1 to n, hi psi c, psi I ci is identically equal to 1. And here you have this variable sits on the boundary and c sits in the omega.
When you say capital Z is an hi of zeta z whole.
It's not capital Z. I assume I know. There. Okay, so the problem is now to find these HIs, which we cannot do in my case. But we'll do a sort of a play around with the same idea. So let me go a little bit back to history here. Sibony, you have an example. Of a domain in C3, bounded in C3, pseudoconvex, smooth boundary, and the closed 0-1 form, closed bounded 0-1 form, omega, but with no bounded u, such that dbar u is equal to omega. So if you don't have any more regularity than just smooth and bounded and pseudoconvex, there is no hope.
Actually, sorry to bother you, but you didn't actually put the u in the dbar u equals omega.
Oh, this is really, okay. Thank you, Eric. You take such good care of me. You take care of my nerves. I appreciate it. All right, let's see if I can calm down and bite.
I don't get on your nerves.
No, you're helping. Thank you. So then there is some more positive results. Let's see here. See the list of names here. There's for convex. But finite type. Then there is several people. So I'll see if I do this the right order. Diedrich, Fornes, Fischer, and Biegering have given a positive answer. And before I go on, let me just tell you what I mean by finite type. There is a whole school of different definitions. Here's my favorite definition. You have a point in the boundary of the domain. We say that the point P is of finite type, or rather of type K, if whenever gamma is a complex curve containing P, and then the order of contact with the boundary or between the boundary of omega and P and the curve is less than or equal to K. So you cannot have a complex curve that has infinite order of contact with the boundary through that point. Now the Sibony example there's one point of infinite type. So okay, so question. Given a domain bounded in Cn, let's assume that all omega is pseudoconvex, and all boundary points are of finite type, which I will say then the domain itself is of finite type. Then can we solve this problem? Given a bounded closed CR1 form, can we find a bounded solution to the dbar problem? See here, is this up? There are some positive answers. So some positive answers, of course, the one about if the domains are convex, any dimension, fine. If omega is in C2, okay, then first, for Ness, solve this problem. Solve the problem on the so-called Kroneberg example. And finally, Range, which is inspired the rest of what I talk about today, solved it for general finite types. So Range solved it for general finite type. In C2.
So when you say solve it, you meant got uniform estimates?
Got, yes, yeah, the answer is yes.
Okay.
Try not to take too much time writing here, but it's lovely, Eric, I appreciate it. Keep at it, yeah. So, okay. So what I want to talk about today is almost 100% complete answer in C3 to this question, except we have run into one little snag, which you don't even know is a snag because we have no example of domains who poses this, this problem. So I want to talk about joint work with Dusty Grundmeier, Lars Simon, and myself with just lovely initials. I can make jokes. So for those who have been in the States for a while, they know this is not the best initials to have. So here we look at domains bounded in C3. We just restrict ourselves to real-analytic. Boundary. And of course, pseudoconvex. And then all examples we can cook up with, and all the examples we have seen, and all the examples we can imagine, the answer, we can solve this problem there. Unfortunately, maybe if I have time in the end, I'll show you the one little snug that maybe somebody can help us with getting rid of. So in most cases, we have a positive answer. So what I really want to do in this talk is give a little sketch of what you will do for general dimension, and then show what makes it special to be in C3, and then hope I can sort of throw the ball to the audience and hope somebody else will catch the problem and find it interesting. So the first thing you meet in when you are in higher dimension than C2. In C2, you have a complex tangent plane, but that's just a complex tangent line. All kinds of types are the same. And moreover, if you go in the complex, there is no way to go. You go in one direction. If you are in higher dimensions, the complex tangent plane will have dimension at least 2. And then you will meet things like type will change as you twist. You stand still in a point and you move, type will jump. And I can say, okay, line type. You move the line and type will jump. Oh, that's not at all the only problem. Also, you will have exceptional curves where order of contact is much higher than any complex lines. So there's a whole lot of more geometry to deal with as soon as you are above dimension 2. So, of course, as always, you jump from C2 to C3. Many more problems, but there are some things that are easier than if you try to go to C4. So I definitely will say there's a lot to be done from C3 to C4. If you want to go, I think up to C6, you'll meet new barriers. But anyway, let me start just by trying to sketch a little bit of the ideas now for general N, and then in the end, show how we can do a little bit or do some of the things in C3. So let me get rid of. So I left that kernel there. That kernel we can just dream of. In fact, you could just forget it. You're not going to be able to create an integral kernel that solves the problem. At least it's a far way to go there. But, so for kernel, first step, we do not know how to solve the Cauchy von Tappe equation. Problem here is we don't know how to solve it and get any kind of regularity in this boundary variable.
You don't have an equation yet.
Oh, maybe you can be my co-writer. Thank you, thank you. Okay, so this is what we do is a sort. This is an idea that definitely is due to Runge. So what you want to do instead, we have color, at least yellow. Instead, you start solving it point-wise. So you pick a point, or pick any point, rather. That was not good. And see if you can solve the following equation. Again, keep in mind we want the functions hi to be holomorphic in the C variable. So now it's really just a function of Z, rather. And of course, we have an index C0, theta naught. Okay, let's say you can do that for every point. Here's a plan. So let's find solutions for every point. Let's hope they look good. Let's leave it like good estimates, whatever I mean by that. And now what you do, give me an epsilon, and then you go in and make a smaller domain. It's another color. You shrink the domain a little bit in a good way. And now you use those point-wise solutions. And this is a beautiful trick, but I'm not going to have time to do it. To actually make a kernel for this smaller domain. So you get the solutions operator on the smaller domain. Tricks. You have good estimates for these functions that will actually translate to good estimates if you replace the psi here with mu in the boundary of omega minus epsilon. This is all in Runge actually, but it's extremely well hidden. So, okay, so that's why I thought I'll mention it. And then you actually do a sort of solution to the Cauchy-Van Tappen equation on the smaller domain. I'll do that if there's time afterwards. It's simple calculus tricks, beautiful. And then you find solutions, U epsilon on omega minus epsilon with uniform estimates. As in uniform in epsilon. And then you use a normal families argument. Pass the solution on omega. Okay? All this is due to Range. What? Yeah, okay. Let me, if you want me to go a little step longer. Let me. Okay, so here, need my white. Psi naught. Omega epsilon, here we just look locally. We look at this function, hi, psi naught, c, and then we do some weird trick. Instead of having psi naught here, we say psi minus c. I. So now it's suddenly a variable in that holomorphic part. Since this is equal to 1 here, then it's not going to be 0 in the neighborhood of this point. Let's call this psi c. Dirty trick, divide by this. Okay, now we have a solution locally. Dirtier trick. Use cutoff function. Make sure you use them just vary in this variable. Does not destroy holomorphicity. Bam, you have a kernel on the smaller domain. Okay? And the point here is, of course, that you somehow could control the estimates.
What kind of domain is Ronald working on? What kind of domain is this working for?
This is working for real-analytic or finite type. I think you just see real-analytic in C2.
Okay,
C2. Okay, so goal, do the same in C3. And the challenge here is, again, you take a boundary point. And now look for these functions. Because in this case, of course, the I would go from, if you're in C2, I is just 1 or 2. But, okay. So these functions hi, psi naught, c. And let's just be in Cn for now, because this is the same approach in any dimension. So that this times psi 0 minus ci is identically equal to 1. That you can do, easy. But you need good estimates for these functions. What you need is estimates for these functions, so that when you go through this trick here, you end up with integrability of this S omega epsilon and uniform integrability. Okay? So what to do? Well, here again, let's see here. Can't just go ahead and do that by hand. And the reason for that, well, if you think, if those of you have read your Kranz or any of the textbooks, several complex variables, seen that if omega is strict pseudoconvex, typically you take your domain, take your point, find a function so that this, the zero set of this goes through the point and avoids the domain. And better than that, it has a nice order of contact here. And as a function of C, you want this to be holomorphic. This is a so-called support function. This is not possible if you are in a bigger category than strict pseudoconvex or convex domains. Because Kohn-Nienberg have an example already in C2 that shoots this idea down. You cannot do it. There are examples of pseudoconvex finite type domains, points in a boundary where there is no holomorphic, even local holomorphic support function available. So we have to be more clever. So what you want to do is instead start with, again I have to say, all the ideas I sort of cook up has been very much inspired by Michael Runge, and talks he's given or things he's done in his paper. So I mean, don't want to forget that. So start with functions G1 up to Gn. We are in Cn for now, which is not holomorphic in C, but they are what can I say? Satisfy good estimates. Again, what do I mean? If they were holomorphic, I put them into this procedure, everything would come out nice and integrable. Okay, and then we need to do something. We need to modify these G's. Yes, I'm looking. I think there should be the zero set of this thing.
So it's holomorphic.
And it's holomorphic as a function of Z. I mean, Kohn-Nienberg example shows that's not always possible, right?
So good estimates means.
If you plunk this into the kernel, do this procedure, you get something integrable. And of course, uniform estimates into integral. I wish I had time to write out what I mean by good estimates, but then we'll not be able to make dinner tonight, so I don't think we want to go there. But it's all on the archive, by the way, so even worse, coffee break. So now what I want to do is just very, very sketchy, tell you a procedure. For now, I'm in Cn, because this works in Cn also. And so here we go. I start out with some smooth functions. That looks good, but of course they don't give me a solution to dbar because they're not holomorphic as functions of C. And then I go through, see how to get to my, because now I need to look in my notes, a sort of Koszul complex, and I think I'm going to say now, Koszul complex-like procedure. Because when I talk to people in different fields about this, I get a different version of what the Koszul complex looks like. So, Koszul complex-like procedure. What's what? I don't know, depending on field. Okay? Because now I want to do is to take my G's, modify, get H1 to Hn, which now are holomorphic in C, satisfying the same estimates. And here what I'm going to do is I'm going to use what's become my favorite Hermann-Derwert theorem. There are many of them. We use L2 estimates. And a theorem of the kind, you have some, zero Q form. dbar closed. You have omega pseudoconvex. Then, of course, omega should be in the appropriate L2 space. I'll leave it open. You'll see in a second in the estimates what I mean. Then I can find a u. Let's see, get this up a little more. Nothing better. Find u such that d bar u is equal to my form, and the L2 norm of u with appropriate weight e rho is bounded not only by some constant, so let's put in a twill here, of the L2 norm of the form, but more than that, there is a help from a matrix here, A inverse omega omega. And that A inverse is there to help me improve estimates. So I gain regularity when I solve the bar. Let's see what I've done wrong now. So, of course. Yes, thank you. So this is crucial in many of the steps I do. And this A will depend on Q. So A depends on Q, and it depends on the weight. If Q is 1, it's just a complex Hessian, A, and then you take the inverse. Okay. Now, okay, so now I will start making myself a hoard of the bar equations. Of course, before I go on, maybe I should just tell you, so I have these GIs, and I would like to modify the GIs. And I can't just solve the bar problem, find some way of modifying them by finding some UIs with good estimates and modify them and get something holomorphic. That's not good enough, yeah? Because I also need, for the modified, the HIs to satisfy that equation up there, the Cauchy-Fantappel-like equation. So you can't just go ahead and modify and happy. You need to keep an eye on getting that result too. So therefore, you have to go through a lengthy procedure. You write up each of the d bar GJs. You realize that they are actually equal to themselves if you multiply them by 1. Now, let's use I here. It doesn't make a difference to multiply by 1. And then you also notice that if you take the bar of the sum of the GIs, you will get something which is, of course, is just d bar, and now it's d bar with respect to z, since we are. And this is, of course, 0, because the derivative of 1 has a bad habit of being 0. Then, using these things, you replace d bar gj minus the j's coordinate here. This looks crazy. By minus the sum of all the others when they are I is different from j. Okay, now I see time is trickling out. So now you end up with some terms. So you end up with some sort of terms we call hij, which will be what? It will be gi d bar gj minus gj d bar gi. So these are 0, 1 forms, not the bar closed. Now you play the game with each of these, and this is the same as and okay, you dig and you dig and you get an explosion of 0, 1 forms, 0, 2 forms, 0, q forms. And 0, 2 equations, the bar equations. In the end, you end up with something real nice. In the end, you end up with a 0 n minus 1 form. Some coefficients, gi, and then the bar g1, the bar gi taken out. These are just coefficients here. And d bar gn. And this guy is now d bar closed. Okay. Yeah? I can write it again.
Is this a delta I or a?
It's just coefficients. So, I mean, okay.
Oh, the delta I are coefficients. I see. Okay. Got it. Oh, bi. That was a bi.
Let me just rename them because then they don't get a sort of, they don't play a more role than they. There are particular coefficients that occurs. And they are so that if I take the bar of that form, it will get 0. Now what do I do? I have my form, what did I call it? It needs a name. Just call it H. I have my form H. Find U such that d bar U is equal to H and satisfies good estimates. Modify, use that U to modify the next, so let's go back. All I can say, go back. Solve all the d-bar problems. You created. On the way. Use different, so use that Hermander theorem. Use different weights in each step. Take advantage of everything you got. And then, if you are lucky, you come back and you can get your HIs. In fact, which satisfy the same estimates as your original G's. Okay, this is of course just a stupid fairy tale. Let's now see a little more concrete how one can take advantage of this approach. Okay, this is a good dream. Let's stop dreaming and start doing something real. See here. First, let's look how we want to choose these GIs. Well, first we start with our domain. Choose our point, size 0. Now we need to look for omega psi 0 star, which is locally. So that this is pseudoconvex. So-called bumping out, which is very crucial here. So you want omega closure minus this point. Again, everything is local here. It's contained in omega star psi 0. So they should have just one point in common, namely that psi 0. Okay. All right. Good. And this is where we're going to solve. So this is where we will do our previous, we'll solve our previous. dbar problems. So on the larger ones. Okay. Next, how to choose the G's. So here first we start with what I would say is a smooth support function. It will be holomorphic in the normal direction. So let's say that is the C1. And then it will not be holomorphic in the remaining directions. Okay, this is normal. So this one actually will be holomorphic here, and G1 will be just 1 over this. And then the other GJs, you have to do a smooth division problem, which we do by hand in our paper. From 2 to n. Okay, go back to the top picture here. We want a couple of things from this phi. Phi equal to 0 should be, except in this point, be outside omega, the bumped out domain. In fact, let me write it here. I have my list here, just a second. Here. I guess with this picture, all I need to say what's really, really, really important is if I look at this function, when C is on the boundary of the smaller domain, here's a bumping to type. This should be comparable with the distance from the point to the boundary of the bumped out domain. That is the hero in the whole game. If you can do that, you're done. The rest is hard work, really hard work, then you're done. And the thing that happens if you choose these G's like that, the form H will just then be looking like the following. Constant times dbar P2 down to wedge dbar Pn divided by phi to the power n.
Let me see, your G's, I think, are hidden behind that.
Okay, I'll put it back up here. Okay. Here, that's the goal. And I don't want to be one of those that drags time out. Do I have 5 more minutes?
Yes, exactly.
Okay, so I have a list of examples. Let me just grab one, which I know there's people that work in this business. This is their sort of the most disgusting example they can think of. So let me show you how we deal with that. The so-called iron cross. Except I Koningbergify it. Because the original iron cross actually has a support function. So I sort of play a little Koningberg game with it. So the original iron cross looked like this. So it's the normal derivative C, W, so let's use this, plus this to the power 8, and then what? C, well, one version of Z to the 20 plus W to, what did I have here, 100. Less than 0. This is one variable, so this is the... So I have 3 variables, I'm C3. So this is, of course, immediately I have a support surface. It's just given by this guy equal to 0. So what I do now, I replace this by a Koningberg example. And so here's the Koningberg example, which some of you might not have seen, so then you get to see it. Except it's just in one variable. I replace one variable by a holomorphic function, so it still works. So. Okay. Then I do similar thing for C in the 20s. I make a Koningberg example in the 20s, the green C, and also one for W in 100. I don't have time to write it up. The point here is that if you make this defining function, you can actually subtract epsilon times norm C times W to the 8, and epsilon times norm C to the 20, and epsilon times norm W to 100 from this defining function. So you have your domain, and get this largest domain. It's still pseudoconvex. Okay, and here's how you choose your phi. Psi minus the large A, norm CW to the 8, norm C to the 20, plus norm W to 100. If you like, let me give you P1, P2, and P3. So P1 was, as I said, equal to 1. P2, let's see here, it is simply, of course, minus A, and then you get Z to the 3, C bar to the 4, norm W to the 8, minus Z to the 9, C bar to the 10, just done by hand. Let's do like this, I get to write A, and then P3, what? Minus A, W to the 49, W bar to the 50. I'm out of time. I have not dealt with curves here, but a large part of the paper is also dealing with curves rather than exceptional lines, because this is where you have type jumping in the different line directions. I think I'll stop there.